Now, with experiments, if we take data from the real world, we download them from the real world, we use data that already exists, even if we collect it ourselves, but we haven't designed an experiment, then that's what it is. We have to analyze it the best way possible, the way we have it. But with experiments, we have the freedom to design it to answer the questions we are interested in. And with this freedom comes responsibility, because we have to design the experiment such that we won't be disappointed at the end of it. Because if we are disappointed at the end of it, not by the result, but by the fact, say, that we find them very difficult to interpret, it's going to be our fault. It's because we haven't designed the experiment properly. So there are very many interesting design questions. We'll get back to them later in the semester. And if I have a little time, we'll go back just to the 3 examples that we talked about last time. For now, we are equipped to ask a very simple question. Suppose you're interested in designing a simple, completely randomized experiment to test the Niemann hypothesis for a particular thing. For example, suppose that I haven't done the experiment yet for the camera, and I want to know what should be my sample size. How large should my sample be? So intuitively, what are the ingredients that goes into that calculation? Like, why do I need to even ask this question?
Well, a very large sample size would be costly, both in time and money.
Right, so we don't want infinite sample size because we don't have infinite amount of money, so it's unlikely to be possible. So that's on the one side. And on the other side, yeah.
It's too small, then we might get a result that's not actually true.
If it's too small, the variance can be large of the estimator because there is some n in the denominator. So the larger the sample size, the lower the variance, therefore the tighter the confidence interval will be for our estimated treatment effect, and the more precision we will have to test hypotheses. So that's exactly the trade-off that we are facing, is how small a sample can I get away with and say something and be able to say something that is going to be meaningful. So this is called the power calculation. So this is called power calculation because the way we think about it is we think about it in terms of an hypothesis we will want to test at the end of the day, and what's going to be the power of our test. And this is our last review of Sarah's last lecture, where we finished by power of the test. So in this case, I didn't even attempt to copy it. I just grabbed it. So for a sample size of n, what we are going to be observing is a treatment allocation for our n observations and the observed outcome. And of course, in order to do power calculations, we must say what is the hypothesis that we are interested in testing. And for the rest of today, I'm going to assume that we are interested in testing the Niemann hypothesis. So the Niemann hypothesis is that it's H0 that the average treatment effect is 0 against the alternative that it's not 0. Little reminder, straight from our previous lecture, if we accept H0 and H0 is true, we are good, there is no error. If we reject H0 and in fact H0 is false, again there is no error. But there are 2 types of error. One is where H0 is in fact true, but you reject it. This is type 1 error. H0 is in fact false, but you accept it. You fail to reject it. So the significance level of the test alpha is the probability of type 1 error, and 1 minus alpha is the confidence level. The operating characteristic of the test beta is the probability of type 2 error, and 1 minus beta is the power. So I call beta not the operating characteristic, but the probability to be disappointed. So it's the probability that at the end of the day, you run your test with critical level alpha, and you don't find anything significant. And so 1 minus beta is the power of the test. When you design experiments, that's really what you're thinking about. What's the chance that that you don't find anything significant when in fact there is an effect. So what ingredients go into the power calculation? So of course we need to pick alpha and beta. Well, either we pick alpha, and then either we pick beta and we calculate the sample size we need, or if for some reason someone has given us the sample size and there is no choice, we can tell them, well, for that sample size, this is what the beta is going to be. Okay, this is a 1-for-1. I'm going to assume that we want a specific beta, we want a specific power, and we will calculate the sample size that we need to reach it. So alpha, we kind of usually don't have much of a choice because society doesn't want to conclude that some treatment work when in fact it doesn't. So we tend to pick alpha low for a high confidence level. Following Fisher, alpha is often 0.05, like Fisher has given us the sort of the magic number of 5%. So so let's say we pick alpha to be 5%. Now, given alpha, you want to pick n, such that if the average treatment effect is in fact some value tau, the power of the test will be at least 1 minus beta for some beta that you decide to reach, given that the fraction gamma of the units are assigned to the treatment group. So another way to say it is you need to pick NC and NT, or given, but we're going to take gamma as given. So in addition, we must assume or know something about the variance of outcome in each treatment arm. We're going to assume that they are the same, and it's some number sigma square. So in summary, for power calculation, we need to know or impose or assume a bunch of things, and then we're going to get n in exchange. So the ingredient that's going to it is alpha. That's typically 5%. Beta, you kind of have more flexibility there because you're just taking the risk. You know, but people usually go for a power of 80%. Tau, sigma, and gamma. Gamma you can decide for reasons that are going to appear to be obvious in a minute when I show you the formula. Unless there is a strong reason to have more treatment unit and control unit, it is efficient to have the same number, as long as you assume that the sigma square is the same. So you're going to assume that you're going to often pick that 0.5, but if you want to pick 0.7, you can just do the calculation with 0.7. And these two here are the sticking point. So this is 0.05, 80%, let's say 0.5. These guys are a bit of a problem. Because where are they going to come from? So that's the problem with power calculation, is that there is a lot of nice formula, but it really is black magic because there are two ingredients that come into it that we don't know anything about. If we knew something about them, we wouldn't need to do the experiment in the first place.